So we're asked if when the switch is closed, what happens to the potential difference compared to when it is open. So I redrew this one. This would be like if it's open, you can basically just ignore this second loop. So this is the circuit when the switch is open. This is the circuit when the switch is closed. And I'm asked specifically about the potential difference or the voltage from point X to point Y. Well, right here, this is just wire right here. So that's basically asking from this point to this point, which is just asking what is the voltage drop or potential difference across this bulb right here when it's open compared to when it is closed. Well, this one's actually really easy because when you're closing it, you're just putting another bulb in parallel. In parallel, all the branches have the exact same voltage. So adding another branch doesn't change this guy's voltage at all. This voltage is just the voltage of the battery. So it's equal to, nothing happens because when you close, so when the switch is closed, it adds bulb E in parallel with the battery and bulb D. Because all voltages, I'll just say delta V, or all potential differences, I'm going to say because the potential difference of all branches is equal in parallel, the potential difference from X to Y has not changed. Some of you might have thought through, well, okay, a lot of people think through, like, before they realize the voltage would just stay the same, they try and think through current. So if you're thinking, well, now the current is splitting in half, as long as they're equal to each other, it doesn't tell me. But let's say they were equal, your current would be splitting in half, but that doesn't mean I have less current through this guy. It just means that I'm starting with more current, which makes sense because when you add resistors in parallel, you get a smaller total resistance, which means I'm getting greater total current. So a way to make up numbers for this is, let's call this 1 ohm, 1 ohm, 1 ohm. Let's call this, 10 volts and 10 volts. If this were the case, this one would have 10 amps. This one would have a voltage drop of 10, so this would also have 10 amps. It means I'm coming out with 20 amps right here. And then here, the voltage drop of the battery is just the voltage drop of the resistors. This is also 10 volts, which means that there's 10 amps coming through the circuit. Part B, what happens to the current through the battery? We already kind of just answered that. It would increase because two ways you can think about this. One way is you can say now there is less equivalent resistance in the circuit because you added a resistor in parallel. And because I is V over R, and we're talking about total current is total voltage over total resistance, less R total with the same total voltage means a greater I total. So greater total current through the battery, total current. The other way you can think about this is you know that the voltage across D hasn't changed at all, so D still has the same current, but now E also has a current, so that means you added in, or like you're starting with more current from the beginning. So, or D has the same potential difference as before, so it has the same current through D, but now E also has a current, so there's more total current through the battery. Right? If before I only had one current through D, but now I still have the exact same current, but I also have a current through E, then I'm starting with more total current, more current through the battery. All right, number 20, at first the switch is open as shown, but then the switch is closed, so I'm going to draw my open versus closed. So open, I've got two bulbs like this. And if I'm closed, what happens when you close this circuit is that now current, instead of going through B, is just going to skip around. It's choosing the easier path. So now I'm going to redraw what my circuit is. This is just wire, so it doesn't make a difference right here. This is like the closed version of the circuit. What happens to the current through bulb A? Well, the current through bulb A at first was the total current of the circuit. Current through bulb A here is still the total current of the circuit, but this is a different total current through the circuit. I think about it as like, okay, I total is total voltage over total resistance. It's still the same battery, so I still have the same beginning or total potential difference, but now I'm dividing by only the resistance of one bulb instead of the two bulbs. So now there is less total resistance or equivalent resistance because current will skip over bulb B because there's an easier path around. And current is always going to choose the path of least resistance. So because there is less total resistance, so, and I'm going to say because I is V total over R total, less R total with the same V total, because the same battery, means a greater total current. So bulb A has more current. Now part B is asking what happens to the potential difference across bulb A. So some of you might say, and you can totally use this, so the voltage across bulb A is just the current through A and the resistance of bulb A. Well, the resistance of bulb A is the exact same, it's the exact same bulb, but now you have more current going through the bulb, so you'll have a greater potential difference, a greater voltage drop over the bulb. That's one way. The way that I went on my answer key was talking about, okay, well, if you look at, let me just explain it before I write it. So here, this is, I'm going to call this like my total voltage, that's the battery. When there was two bulbs, then they had to split the voltage because the total amount, or like the sum of voltage in a closed loop adds up to 0. So whatever voltage I started with, these each add up, their voltage drops add up to the total voltage. Here, if I start with the potential difference of V total, well, it's only dropping over bulb A, so that means the voltage drop over bulb A is the total voltage. Alright, so I would have gone that route for the explanation for B. So what happens to the potential difference across bulb A? We said it would increase because now the potential difference of the battery is all, what's the right word for this? I want to say used up, but what did I say in my key? Yeah, I said dissipated. Is all dissipated on bulb A, whereas before, the voltage of the battery was split between bulb A and bulb B. And our reasoning there, like the rule we're using there, is the Kirchhoff's law about the sum of voltages. So let's go ahead and say, like, why is all of this all in A, whereas before it was split between? And then reasoning or like the rule we're using here is because the sum of voltages. So because the sum of voltages in a closed loop must be 0. Alright, what happens to the potential difference from X to Y? So from this point to this point. So what I said is that now, you definitely have current going through X and Y. Before, the potential difference was just the voltage. When this is open, this is right in my diagrams. Yeah. So when this is open, this is just saying like potential difference from here to here. Well, that's just the potential difference of the bulb B. But now the potential difference is of the switch, bulb here, or you could think about it as a potential difference bulb B, which nothing is going through. Either way, you're going to get 0 potential difference here because none of that voltage or that energy is getting used up in here. So you should say it decreases to 0 because now current has no resistance in the switch, or you could say like no resistance or very, very little. So I'm going to insert that. It has no or very, very little resistance. That doesn't look like very. So because it has essentially 0 or very, very close to 0, very, very low, because it has no resistance, there's no potential difference across the switch. Another way to say that or think about this is, well, if your total voltage is being used up by bulb A, now there's no voltage drop in the rest of the circuit because all of your voltage is being used up for bulb A. So what I wrote in my key is it decreases to 0 because there is 0 or a very small amount of resistance in the wiring switch. So if you have 0, very little voltage across bulb B because the voltage is I times R. So if this is essentially 0, then that will essentially be 0, even though you might have a lot more current. Okay. What happens to the potential difference across R1 when the switch is closed? So R1, the potential difference, I'm going to call it potential difference 1, is just current through 1, R1. So R1 might stay the same, but the current through 1, which is just the total current, has changed because I've changed the total resistance of the circuit. In fact, when I add in this second resistor in parallel, I'm decreasing so you're going to decrease the R total, or the equivalent resistance of the circuit. So that's going to increase the total current. So you're increasing the total current because you decrease R total of the circuit when you add resistors in parallel. So because R1 has more current through it, and voltage drop equals I times R with the same resistance, R1, it will have a greater voltage drop. So the idea here, if you're like, wait, but you just said resistance decrease. Yeah, the total resistance of the circuit has decreased, which means I have more total current because total current is total voltage over total resistance. I'm keeping the exact same battery, so the same total voltage, but I'm dividing it by a smaller amount of total resistance, so I have more current coming through. And if more current comes through this specific resistor, more current right here, times the exact same resistance as before, then I'm going to get greater voltage drop across this resistor than before. What happens to the potential difference across R2? Now, it's very tempting to be like, oh, these are in parallel, it stays the same, but that's not true. These two have the same voltage. That doesn't mean it's the same voltage as before. So you could do the math here, or you could say, you know that the sum of the voltage across 1 and the voltage across 2 must add to the voltage of the battery, so voltage of the battery. And then your reason here is just Kirchhoff's law of of voltage, which is the total. You could just state the sum of voltages in a loop, closed loop, must be 0. So if you're provided V, then this drops and this drops back to 0. So these two must add up to the total you're provided with, or you could just call it Kirchhoff's voltage law or law of voltage. That sounds kind of weird. That's okay though. Anyway, you know that these two voltages still have to add up to the same total. So because the voltage drop across 1 increased, but you still have the same total voltage or battery voltage, then the voltage drop across 2 must have decreased. If you're like, wait, but there's more current in the circuit, that's true, there is more current, but then it's getting split up here. And it's not twice as much current coming through, so when it has to split in half, it's still less than before, so then it has a little bit less voltage drop. And then these two have the same voltage drop. But I wouldn't add all three to get to 0 because one closed loop is just this voltage drop with one of them. It doesn't matter which one you add. Alright, 22, each resistor represents a bulb with resistance R or 2R. If the battery in the first circuit delivers a power P, determine the power the other batteries deliver to their own circuits in terms of the original power P. So I have these drawn. Perfect. Alright, so we are looking for the total power, or the power of the battery. So P total is just I total, V total. And we know all of the voltages. So all of the voltages for each battery are going to be the same. So really what we're concerned about is like the total current through the circuit. Not necessarily individual currents, but the total current through the circuit. That's what's going to be the easiest to find total power. So I'm just going to say, if we're saying this one has power P, let's just call this current I. And then we'll just do everything else in terms of the original. So if this is voltage divided by one resistor, that gives me current. If I have the exact same voltage, but now I'm dividing by 3 resistors, that means that I have 1/3 of the current, because instead of V over R to get my I, now it's V over 3R, so that's 1/3 the original I. Alright, here, same voltage, but over 2 resistors, so that would be half the current. And then here, so you can find our total. I just found it easier to find each individual current. So this is V over 1R, so that's just I. V over 2R, that would be half the current right here. So then if you have half of I coming in this way and 1 I coming in this way, that means you're starting with 1.5 I from the battery. Right, now I know my voltage for all of the batteries, it's V, and I know my current for all the batteries, it's I, 1/3 I, 1/2 I, and 1.5 I. So P equals IV here, P equals 1/3 I with the same V, P equals half I with the same V, and P equals 1.5 I with the same V. So if I'm calling this